Hi, welcome to this poster presentation. My name is Karina Hernandez and I'm studying the second semester of the doctorate in environmental science at Toluca Technological Institute. It is my pleasure to present the progress of my research project entitled Hydrogel of carboxymethyl chitosan obtained from the chemical modification of chitosan and their characterization. Carboxymethyl chitosan is a derivative of chitosan. It's biocompatible, non-toxic, biodegradable, soluble in water in a wide pH range, and it has some application like in cosmetic, food, and pharmaceutical industries. Here we can see the reaction between chitosan and monochloroacetic acid to obtain the carboxymethyl chitosan, the CMC. It's very important to mention that depending on the reaction condition, different products can be obtained, such as OCMC, the NOCMC, or NCMC. The main objective of this work is to modify a commercial chitosan through carboxymethylation reaction to obtain a highly water-soluble material for applications as a hydrogel in the control release of drugs. This diagram shows the methodology that was followed in this work. We present the following results. Carboxymethyl chitosan was synthesized using two protocols varying the proportion of the reagents, the reaction time, and the reaction temperature. In method 1, the carboxymethylation reaction was 4 hours at 50 degrees Celsius, while in method 2, it was 1 hour at 30 degrees Celsius. Like we can see in the figure 4, in both approaches, the sodium salt and the protonated form were obtained. The samples were then dried at room temperature or in an oven at 50 degrees Celsius. Figure number 5 shows a photograph of the soluble and insoluble part of the CMC. Figure number 6 is an example of the degree of substitution of the CMC, also referring to its different derivatives. As we can see in Table 1, for the degree of substitution, only the appropriate methodology was determined for sodic samples, so the other samples were reported as not determined. We can say that the sodium sample synthesized by the method 2 and dried at room temperature was the most soluble in water. These results correspond to the degree of substitution, which is around 50%. Figure 7 shows the comparison of the infrared spectrum for the sodium and acid samples obtained by method 2, compared to commercial chitosan. The main changes can be observed at 1596 related to sodium carboxylate and at 1737 related to carboxyl group. Figure 8 shows the proton nuclear magnetic resonance spectrum for an acidic sample obtained by method 2 at 4.6 and 3.92 parts per million, corresponding to OCMC. The chemical shift at 3.29 parts per million suggests the substitution in the amino groups, corresponding to NCMC. Conclusion. According to the percentage of solubility and the degree of substitution, method 2 is preferable for the synthesis of the CMC. Analysis by infrared spectroscopy and proton nuclear magnetic resonance confirm the modification of the material, identifying the presence of the O and M CMC species. Finally, it is necessary to purify sodium samples to analyze them by carbon nuclear magnetic resonance spectroscopy too. I thank CONACYT for the scholarship award The authors also thank TechNM for its support through the corresponding institutional project. Finally, we thank the Macromolecules Radiation Chemistry Laboratory of the Institute of Nuclear Science of the UNAM for the support provided. There are some references used in this work. Thank you for your attention. If you have any question, please don't hesitate to contact me.